Okay, good morning, everyone. Bonjour à tous. I will start with a few words in French and I'll continue in English. Je suis heureux de vous accueillir dans ce séminaire général qui nous est présenté par Gerd Mutschke, qui est en visite à Paris. Et comme d'habitude, comme nous avons un certain nombre de personnes dans l'assistance qui ne sont pas francophones, nous allons faire le séminaire en anglais et je vais faire aussi la présentation de Gerd Mutschke en anglais. So we are pleased to welcome today Gerd Mutschke and Mengyuan Huang. Mengyuan, you raise your hand. Maybe online you cannot see Mengyuan yet because she is sitting on the side here. So Gerd Mutschke works at the HZDR, Helmholtz-Zentrum Dresden-Rossendorf, which is a center working in particular on the energy transition with lots of fluid mechanics in it. And Gerd did his PhD with Jochen Frohlich in Dresden. And before that and after that, he worked for the HZDR, also near Dresden. Mengyuan Huang did her PhD in part with Gerd Mutschke and with officially with Karsten Eckert. And she also was going to present this seminar on magnetic control of flow and mass transfer in weakly conducting fluids. Let me add that I'm very happy to welcome Gerd and Mengyuan. We have a lot of interest in common, especially for using Basilisk for multi-phase flow. And maybe Gerd will have the time to talk to you about it. Gerd will be here today and tomorrow, and Mengyuan will stay for maybe 3 weeks approximately, so you will have also more time to talk to Mengyuan afterwards. Thank you. Please start.
Thank you very much, Stefan. Thank you first of all for inviting us and hosting us here and giving us the opportunity to discuss with you and your group. The title of my talk is on magnetic control of flow and mass transfer in weakly conducting fluids like electrolytes. But before coming to that, maybe I give a very brief introduction on our center and the research association we belong to, which is the Helmholtz Association, which is a quite large body in terms of funding, and it operates 18 research centers in Germany. Some of them are quite large, like KIT, you might know, or Forschungszentrum Jülich. We are only of about mid-size. We are located near Dresden, nicely in the forest. On the eastern part of Germany, we have a staff of about 1,500 people, including scientists, doctoral students, and technicians from more than 60 nations. Our research center is structured into different institutes that work in different fields of science. So the first field of science is the energy research, and we are especially concerned with the resource and energy efficiency of processes there. There's a large number of institutes that deal with research of materials under extreme conditions, for example, extremely high magnetic fields. And there are also 2 institutes which are dedicated to improve the radiation therapy for cancer diseases. Our Institute of Fluid Dynamics is headed by Karsten Eckert and Uwe Hampel since last year, and there are different fields of activity going on in our institute. We have a staff of about 120 people, so we are concerned with complex two-phase flows in energy and process engineering. We study wastewater treatment, also the energy efficiency of this, which is quite important for municipal bodies, and we develop advanced measurement techniques for those complex multi-phase flows, for example, X-ray tomography methods. We have an CFD department which is supporting these experimental activities. Here a picture is shown for flotation process, which is being used in industry to extract minerals from ore particles that have been milled before. We have a big magnetohydrodynamics research activity which deals with the interaction between the flow of conducting liquids and the electromagnetic fields that are applied. You know, there might be cross influences of both due to induction. An extreme example on that is this Dresden facility that is depicted here, which has a size of about 4 meters height and which precision-driven dynamo experiment. So in that experiment, you have a cylinder filled with liquid sodium, and that is just being moved, and by this motion of the liquid that is resulting and external disturbance of the magnetic field, you try to generate magnetic fields. This is of relevance for astrophysical processes, so our research does not only concern metallurgical application, but also those larger scales. And the field of research of transport processes at interfaces is studying these flotation processes. We are especially interested in water electrolysis processes from the simulation point of view, and another field of activity are these rare earth element extraction technologies, which are also of strategic importance for the countries nowadays. So in the outline, I will give a bit more broad introduction on the topic because of the audience that we have here, and then I will mainly talk about the utilization of Lorentz force and magnetic gradient forces in order to control the flow, and then we will end up with a summary with respect to the magnetic gradient force. Here, Mengyuan will take over. In the introduction, I start with a general slide. So actually, the field of research is close to the magnetohydrodynamics in general. So we are looking at the effect how magnetic forces can influence the flow of liquids. So I put here on the upper left corner the Navier-Stokes equation for an incompressible fluid. And then from externally applied electric and magnetic field, there's an electromagnetic force density resulting, which consists of an electrostatic part and the Lorentz force part itself. If you have a liquid that is electrically neutral, then that term vanishes and you are left with this part. For this part, you have to get to know something about the current density J, and this is defined by Ohm's law in moving media. In these moving media, you get an additional term that results from the motion of the liquid itself. And the cases that we are dealing here is where this induced current density is much smaller than the electric field that we apply. So we are left with this left part. And then for those of you who know a bit in electrodynamics, there's also an induction taking place as a result of a current flowing through a medium, and this generates induced magnetic fields, but in our case these are much smaller, so we are basically left with the current density and the magnetic fields that are applied to the liquid. With respect to the electrical conductivity, I have to mention we are in a range of 1 to 50 Siemens per meter, which is rather low compared to, for example, liquid metals, which are 6 orders of magnitude more conducting. And as soon as it gets to media that are magnetizable, you have to live with a second force, which is the so-called magnetic gradient force, and which comes into life as soon as you do have inhomogeneous magnetic fields. And you can have considerable magnitudes of those fields. Nowadays in lab experiments, you see on top the magnetic field of a brick-like permanent magnet made from neodymium iron bore, which has a quite strong remnant magnetization and which can generate magnetic fields in the vicinity of half a Tesla, close to 1 Tesla, which is quite a lot. So this magnetic gradient force goes with the magnetic susceptibility of the solution. And this magnetic susceptibility consists of all the constituents inside. So it depends on the local concentration of species that you might have inside your electrolyte. This can be ions in case of electrolytes. And the major part or contribution to this sum here typically comes from metallic ions. Some of them are diamagnetic. They have a negative susceptibility. Most of them are paramagnetic. You have a strong paramagnetic impact from ions that belong to the iron group. And for the rare earth elements, it's even much stronger. I want to stress that for the liquids that we have in mind, because these are all small numbers at typical concentration, the magnetic susceptibility of the solution is much smaller than 1. And then we can, how to say, for convenience, go with this formulation of the magnetic induction instead of the magnetic field strength. And then I would like to say a few words about electrolysis processes in general. So electrolysis processes are processes where you drive a reaction by the help of electrical energy that you add to the system. So you submerge 2 electrodes, you apply a voltage, and then something happens at these electrodes. What is being sketched here is a process of copper refining. So you have an anode which consists of copper. You have a copper sulfate electrolyte inside. This is dissociated, so it consists of copper and sulfide ions. And then by applying the voltage, you are dissolving copper on the anode side and you are depositing copper on the cathode side. This has importance in industry, in refining copper that is being produced by other metallurgical processes, and then these anodes that are being refined contain impurities, and these impurities then settle down at the bottom of these cells. With respect to the electrical current that is flowing inside the cell, this is a sum of the fluxes of all the ions that are being involved here. So you have a migration term because the ions are being charged, so they move in the electric field. You have a diffusive part and you have an advective part because they are moving with the liquid. And the processes are typically operated at the maximum current that you can get before further reactions take place that you don't want to have, for example, in gas evolution in those cells. And then the limit itself is defined basically by the thickness of the concentration boundary layer at the cathodes. So this is similar to heat transfer or to other things that you might know. So the thickness of this concentration boundary layer limits or defines the mass transfer. And the idea of magnetic control is nothing but forcing a flow to modify the thickness of this concentration boundary layer. And electrolysis processes are quite attractive with respect to the Lorentz force because the electrical current is already inside. You only need to add magnetic fields. Okay, what I forgot to mention is that because of this electrochemical reaction, the concentration of species is changing in the cell, and then there's a little buoyancy force that might come up. And because the copper ions are the most heavy constituents on the cathode, you would see an upward flow, and on the anode you would see a downward flow. This will come into play a bit later. First, I would like to show you some examples of the utilization of the Lorentz force. And first, a very popular thing, some of you might have known this, might have seen this movie of Red October, where a submarine was equipped with a magnetohydrodynamic thruster. Okay, so it works like this. You have a channel or a duct, you apply an electric field to drive a current through the volume and a magnetic field perpendicular to it in order to generate a flow like this. Okay, by applying this, you can propel the ship. In order to achieve reasonable thrust, you typically need very high magnetic fields, and typically superconducting magnets are being used and actually were used in an experiment that the Japanese did in the 90s, where one could really see that the ship is moving. However, the critical aspect of that story is that the efficiency is still low, as the power loss, the ohmic losses in the liquid, they scale with the square of the current density divided by the electrical conductivity of the medium, which is low and which makes this dissipation large. You can do it a bit better by applying only boundary layer control. So this is all relatively old ideas that came up in the 60s. So you can generate an electromagnetic actuator consisting of alternating arrangements of permanent magnets and electrodes. And by the cross product of the field lines, you generate a streamwise Lorentz force that in wall normal direction is exponentially decaying. And this can be used similar to blowing or suction at airfoil. In this case, it is, of course, flaps in order to enhance the lift. And at that time, we had indeed a project with industry, with shipbuilders in Germany, who wanted to replace a stabilizing flap that consisted of two parts in order to generate a high lift by a single flap. And we were researching the use of those electromagnetic actuators. And here I show you a simulation result for this steady control. You see in a laminar flow regime the flag beam inclined without control, and then on the upper side you see this recirculation, which is called stall in aerodynamics. So the lift in that case is rather small, and if you energize the boundary layer, then you can reattach the flow and enhance the lift considerably. I have to mention that this is also not for free. You have to add reasonable amount of momentum that scales, or that has to be compared with the inertia of the liquid. So in order to have a momentum coefficient in the order of 1, you need to balance the flow velocity squared, which makes it expensive at high velocities as well. Now I come to another example, which is a bit related to electrolysis that we did a while ago, and because of that I want to give a very brief introduction. So in water electrolysis, you try to split water into the gases hydrogen and oxygen, and the efficiency is not at 100%. There are losses which are partly related to the existence of the bubbles residing at the electrode or being present in the volume of the electrolyte. So what you want to do is you want to shear these bubbles quickly away from the electrode, and you want to advect them quickly upwards out of the region of interest in order to enhance the efficiency. And in order to study how this could be achieved by magnetic forces, we
I squared. I is the horizontal, right? The current.
Yeah.
So the ohmic loss should be current squared, but the lines around the red regions are linear. So
yeah, I cannot comment on that at the moment. There are several sources in literature where typically, how to say, you see curves like that. It might, I don't know, also depend on the magnitude before you see this quadratic increase, but I'm not sure.
the size of the conductor is the
Could be, yeah. Okay. So in our little experiment, we studied the evolution of bubbles on a microelectrode and applied a surface parallel magnetic field. This gives rise to a Lorentz force, which basically, due to the vertical component of the current density, shears the bubble away. And you see here experiments that were performed by colleagues of mine, where you see here the contours of the bubble growing with time and being slightly displaced in the direction of flow until eventually it departs. And you see here the departure diameter versus the magnitude of the magnetic field applied, and you indeed see a nice decrease in departure size that you can achieve. We did also simulations for that. You see here the shear flow that is being generated around the bubble. We have a nice match with experiments, and the resulting shear force we could estimate at a magnetic field strength of half a Tesla, which is reasonable for these permanent magnets, which approaches the value of the buoyancy force itself. So you can achieve something. Last example for the Lorentz force is trying to make the deposition of metal more uniform. That would, for example, if you have to plate a large area, that would save a lot of material for you. And here I come back to this copper refining cell, and as I already mentioned, you do have a buoyant flow in these cells, and because of this buoyant flow you get a vertical stratification of the electrolyte, and this stratification leads to an inhomogeneity in the current density. So on the cathode side the current density is lowest on top and maximum on the bottom. In order to apply magnetic fields, we first started with homogeneous magnetic fields. They don't work very well, and the approach that we followed later on are tailored magnetic fields, where you apply horizontal magnetic fields that are changing in magnitude and direction across the cell. So this ensures that the force that you apply is always parallel to the buoyancy force that you have in the region near the electrode. And this indeed works nicely, as you can see here in the simulations or in the experiments, which both match. You see this vertical swirling flow that you generate. You end up with a nearly homogeneous concentration, except these corner regions where you have a bit of recirculation, and you can considerably enhance the homogeneity of your deposit. So this is a deposit thickness that was measured experimentally for the strongest magnetic field in that case, and this is a simulation result for the current density in such a cell, which matches qualitatively. Okay, with this I want to come to the utilization of the magnetic gradient force, and here I only want to talk about structure deposition. That research from my side, I would say, was a bit driven by experiments that were performed by electrochemists colleagues in Dresden we were cooperating with. And what you do is you have a cathode underneath which you apply magnetic elements. This can be either permanent magnets or magnetized wires. And if you do a deposition on that, then you get effects that above these magnetic elements you get an elevated thickness of the deposit. So that could be used for creating structured deposits. Here the experiments are in a range of 1 millimeter size of these magnetic elements. And the question is, why does it happen in this particular case? Because it contradicts a bit the original picture that one would have from the magnetic gradient force. So here the copper sulfate concentration is relatively low. The susceptibility of the solution in total is negative because the diamagnetic character of water is dominating. So intuitively one would expect that fluid elements are being repelled out of the region of high magnetic field, but obviously the opposite happens, because there's a downward flow enriching the boundary layer, and then moving radially outward along the electrode. The explanation of that is from the fluid mechanical side of view. So every vector field can be decomposed into a potential part and a rotational part. And this potential part is basically balanced by the wall pressure. So what you have to look at is the rotational part of the force. And if we do so, then we see that the rotational part has to do with the cross product of the gradient of the magnetic field and the gradient of the species concentration. And that gradient of the species concentration initially is directed vertically. You have a uniform deposition initially, but the magnetic element creates gradients in horizontal direction underneath the surface, which then feeds this cross product and creates a curl that sucks the fluid downward and leads to this enrichment and to the higher deposit there. Things are getting a bit more complex when the electrolyte is more complex, especially when you add inert magnetic ions in a supporting electrolyte, which is quite common in electrolyzers in order to keep the electrical conductivity constant. So this is a summary of experiments that was performed by my colleague Christina Schulich and also the group of Michael Coey in Dublin at the time. And it summarizes the behavior that you have in 4 cases. So this is the copper case we just talked about. This is what you get when you add manganese ions in excess to the electrolyte. So you get an inverse structure. For bismuth, as this is diamagnetic and the susceptibility is quite low, you don't see anything in the experiment. But if you add these magnetic ions, then you get this inverse structuring again. And the question is how to explain it. And I don't want to go into very detail. I only want you to take home that electrical neutrality acts in such a way that even for inert ions that you add to the electrolyte, there might be a concentration boundary layer developing at the electrodes. And this is indeed the case for the case of the copper and manganese ions. As you can see, the slope of the concentration boundary layer is opposite to the one of the copper ions on the cathode. And then if you look at the curl of the Lorentz force again, then this term here is dominating, and this is, and because the sign is different, the curl is getting a different sign, so the flow direction is being reversed, and you suck electrolyte along the deposited layer, and then it leaves at the magnetic element, and this can explain this inverse structuring that you get. The same holds true for the bismuth case, and here we did simulations in order to prove that our reasoning really holds true. And indeed, you see the flow towards the magnetic element on the copper side and away from it in case of the combined electrolyte. If you integrate the electrical current density over time, you come to the thickness of the deposited layer. So this is the copper enhancement, this is the bismuth, and this is the inverse plating for the 2 cases where the manganese ions were added. With this, I am done, and I would like to hand over to Mengyuan.
So hi everyone. From now on, I will go in more details magnetic structuring and explore whether and how the magnetic field could support the growth of nanostructures. First of all, I'd like to show 2 simple examples of the nanostructures. Here you see a photo taken by my mom, and in this season, the lotus flowers are growing a lot in my hometown. You can see in the photo that the leaves are quite clean. And this is the famous lotus effect, and such self-cleaning function of the leaves is related to the microscopic structure of the leafed surface that consists of a lot of cone-like structures. And another application in the field of electrocatalysis, as introduced by Gerd, during water electrolysis, hydrogen bubbles could form and stick to the electrode surface, covering active reaction area. And it is found that if the electrode is structured in the conical shape, then they could accelerate the detachment of the bubbles and enhance the reaction efficiency. This makes it such kind of structures, and I focus on the cones, quite attractive, but it is challenging to synthesize them. And among different methods, electrode deposition is a simple and convenient way to produce structured layers. Here we have a sketch. On the top is the anode, on the bottom, the orange part, the cathode. And metal ions, showed here the copper ions, that dissolve into the electrolyte, and as soon as the electrochemical cell is connected to the power station, the metal ions will move towards the negatively charged cathode, where they capture electrons and deposit as solid metal onto the cathode surface. So the key problem here is how to control the metal ions to deposit into the desired conical shape. One could either use a template, or instead of the template, adding some capping agent into the electrolyte. So these are just molecules that will absorb onto certain crystal faces on the deposit and block the growth into this direction, so that the deposit will have a directional growth into a conical shape. Compared to the template method, the one-step method is quite convenient and it's easy for industrial scaling up. But capping agents usually contain chloride that could be harmful for the environment. So in my work, inspired by previous works of the magnetic structuring, I tried to use the magnetic field to support the growth of the conical structures, which could reduce or even avoid using the capping agent. To understand how the magnetic forces work here, we need to keep in mind that there's no ideally smooth surface. There's always some initial roughness, some valleys and hills that look like a little bit like the tiny cones at nanometer scales. And if the surface is made of ferromagnetic materials like iron or nickel, which are also often used in the water electrolysis, then they will be magnetized if placed in an external field. And high magnetic gradients will be created near the tips of these cones. So similar to previous works, we hope that here a magnetic gradient force will also come into play and bring the bulk electrolyte downwards towards the cathode surface, therefore enhance the mass transport of the metal ions toward the cone and support the cone growth. The difference to the earlier works is that here we don't need an external magnetic template. We don't need additional magnetized iron wires or small permanent magnets. The magnetization of this conical cathode itself could serve as the intrinsic magnetic gradient template. In addition, the Lorentz force also comes into play because the current lines, they always tend to enter the cathode surface in a perpendicular direction. So around the cone, you'll see these red arrows, the current density that is bending towards the cone. And together with the vertical external magnetic field, we end up with the Lorentz force that is coming out of the screen at the left side of the cone and entering the screen at the right side of the cone by its definition. This then results in a rotational flow around the cone. And if the fluid element is rotating around the cone, due to centrifugal forces, they also tend to move outwards to leave from the center cone axis. And due to continuity, the bulk upper fluid will come downwards to supplement this outward motion due to centrifugal forces, resulting in a downward secondary flow of the Lorentz force. Therefore, although we don't know exactly yet we could expect that the both magnetic forces might generate such a beneficial flow and support the cone growth. And I'd like to explore this step by step. First of all, we used optical measurements of flow and mass transfer and combined with numerical simulations to study the cones at millimeter size. This gives us a basic idea of the forces, flow, mass transfer, and reaction around the cone. And then moving towards micro and nano scales, where the optical measurement becomes difficult, I performed numerical study to see the scaling behavior of the flow and mass transport when the cone size shrinks. And finally, we could get some insights for the growth of the nanocones. So I focused on the numerical side, and I want to make the assumptions I made in the simulations very clear. First of all, we use continuum hydrodynamic model, applying the Navier-Stokes equation instead of calculating the motion of each fluid molecule. And also for micro and millimeter size cones, during the typical deposition time in the experiments, the deposit thickness is much smaller than the cones, so we could fix the cone geometry in the simulations. In addition, the electric double layer and the magnetic domain are much smaller than the cone, so we could apply electroneutrality and the bulk magnetic materials in the calculations. So now we come to the results. We start from a weak magnetic field and deposit on a couple cone of millimeter size in a vertical uniform field of 60 millitesla. So in the left, you see the simulation, and right is the experimental results of the flow pattern around the cone. You'll see that indeed we have this Lorentz force around the cone, but we didn't see the downward secondary flow from the Lorentz force. In opposite, we see an upward flow. And by adding and closing certain forces in the simulations, I realized that this upward flow is caused by the buoyancy, because it's introduced by Gerd during the simulation, during the reaction, the metal ions are consumed around the conical cathode. So with time, a concentration boundary layer with decreased electrolyte density builds up, and this local light fluid tends to move upwards due to buoyancy. This upward buoyant flow will transport the concentration boundary layer also upwards, as you can see by the optical measurement of the concentration distribution of the metal ions. And if we plot the concentration profile along this white arrow, we see that in the experiment simulation, we get good agreement, and on the left side, the result around the cone tip, we have decreased concentration. This means that in this case, the magnetic forces are too weak, and the buoyancy force is dominating over the secondary flow of the Lorentz force, and it could not enrich the metal ions around the cone tip, and it's not desired for cone growth. So in the next step, we try to enhance the magnetic forces using a higher magnetic field of 200 millitesla, and we also consider iron cone, which is ferromagnetic and can be magnetized, so that the magnetic gradient force also comes into play. These figures show the distribution of the concentration and also the flow velocity by the black arrows. The left two figures are quite similar to the last slide, that the upward buoyancy is dominating. So for the couple case, the Lorentz force indeed is quite weak, and it lost its competition to the buoyancy. For the iron, due to the additional magnetic gradient force, we get a downward flow from bulk towards the upper part of the cone, which is counteracting with the upward buoyancy developing from the bottom of the cone. And this counteraction results in a jet-like flow leaving from the surface. We see in the red circled region that the concentration boundary layer is very thin because of this downward flow, and high concentration gradients and enhanced mass transport can be expected. This is shown by the result of the distribution of the deposit thickness along the cone. At the left side of the plot, it's the deposit thickness at the cone tip. For the case with iron, it's almost 2 times larger than the other two cases. The downward flow caused by the magnetic gradient force was later on also measured in the PIV experiment by my colleague Lucas Koser at TU Dresden. So the left 4 figures show the distribution of the depth flow velocity and the vertical flow velocity. So the depth flow velocity, it is going inside the screen and coming out on the right side of the cone, and this represents its rotational azimuthal flow from the Lorentz force. And the bottom 2 figures are the downward flow caused mainly by the magnetic gradient force. On the right, it's the flow velocity around these horizontal red lines, and we also get a nice agreement between experiment and simulation. And Lucas also constructed 3 cones arranged in a line in the experiment, where he modified the distance between the neighbor cones to study the possible neighbor influence. Because if we think of a material surface that consists of a lot of micro and nano cones, then the neighbor cones could actually interact with each other. So in the middle, you'll see the characteristic azimuthal flow velocity caused by the Lorentz force as a function of the cone distance. If we look at the horizontal axis, this infinite sign represents the case with only one single cone. From right to the left, the cone distance decreases from 3 multiplied cone diameter to 1.5 cone diameter. And with the decreasing cone diameter, cone distance, we have decreased azimuthal flow velocity. On the right is the vertical flow velocity from right to left. Again, we have a weaker flow if the cone comes closer to each other. But even at the smallest cone distance considered here, we still get a negative sign of the velocity, meaning a downward beneficial flow. So we see that the magnetic gradient force is quite promising. It could generate such beneficial flow and enhance the mass transport, even when the neighbor cones come closer to each other. And the next step is to see how this effect changes when the cone size shrinks. On the left side, you'll see the characteristic azimuthal flow velocity as a function of the cone size in a logarithmic plot. So for both carbon and iron, it follows a uniform slope equals to 2. And on the right side, the vertical flow is more complicated. If we look at the red and green lines that are caves without magnetic field and the couple with magnetic field, we realize that they overlap with each other when the cones are smaller than 100 micrometer. This means that for smaller cones, the Lorentz force is also not bringing any influence at all. It is dominated by the buoyant flow, which is decreasing very fast with the cone size. The black line is a case with the iron cone with the magnetic gradient force. The flow is decreasing more slowly, following a slope of about 2. So now we want to understand why are these scaling behavior? Why are these slopes? If you still remember, Gerd has explained that only the rotational part of the force is actually driving the fluid motion. So here we try to balance the rotational part of each force to the rotational part of the friction. And this enabled us to derive, theoretically, the scaling behavior of the flow caused by the Lorentz, the gradient, and the buoyancy force separately that scales with the cone size with the power of 2, 2, and 3, respectively, that corresponds to the simulation. So this scaling law could be quite useful because optical measurements, they could measure the flow of a cone or similar structure at millimeter or large micrometer size. And by applying this scaling law, we could get an idea of some order of magnitude for the flow around the similar structure, but at nanometer scale. So we see that with smaller cone size, the beneficial flow is getting smaller, which can be expected. And the next step, I try to enhance to support this beneficial flow at smaller scales. I tried different electric and magnetic fields and plot the deposit thickness along the cone for different situations. So these different colors represent different electric fields, and we see that the largest structure is obtained by the red color. That's a pulse reverse deposition with high currents. On top of that, applying a magnetic field could further enhance this structuring of the cone. So finally, I will apply the knowledge obtained until now and analyze the nanocone growth experiments by our collaborators, Kasia and Jota, in Poland. So here is the experimental setup with the working and counter electrodes oriented parallel and in vertical direction. On top of the working electrode, if we zoom in, we will see a lot of small nickel nanocones, so that the magnetic forces and the flow that analyzed before are also expected here. However, Kasia could not measure an enhanced cone growth actually when the magnetic field is applied. Actually, she sees more smooth surface and the cone tips seem to be less sharp in the magnetic field, which we want to understand why. By separately calculating the local flow near each nanocone and the global flow in the entire electrochemical cell, we could give a possible answer to that. On the left, you see the flow around the entire working electrode of about 1 centimeter size. You see this rotational flow and the electronormal flow that is typical of the Lorentz force. Indeed, this flow is caused by the bending of the current density towards the edge of the working electrode that, together with the perpendicular magnetic field, results in the global Lorentz force. On the right, you see the local flow near one single cone, and we do have this beneficial flow velocity that is on micrometer side. However, if we put two flow into quantitative comparison, we realize that the global flow is much, much stronger than the local flow. This is critical for the result, but it's actually usually neglected in the experiment. So we try to enhance this. We use the enhanced setup. We arrange a Teflon ring around the working electrode. Because Teflon is electrically insulating, the current densities are supposed to enter the working electrode in the perpendicular direction. Then with the perpendicular magnetic field, the Lorentz force should be minimized. Here we see the distribution of the flow pattern in a vertical plane. Compared to the left figure, the working electrode, the cathode. And here we see that in the enhanced setup around the working electrode, the flow is much weaker. So the scale bar here is different. However, it is not disappearing. This is because around the counter electrode, there's still some bending of the current density and some Lorentz force. Actually, in reality, it's quite difficult to completely suppress the global flow. But we can reduce it by proper experimental design, as shown also on the right. The average concentration at the working electrode with the enhanced setup, we have a lower concentration, meaning reduced global mixing. And in the end, we got the enhanced surface roughness of about 50% that indicates higher cones and enhanced structuring effect. So this brings me to the end of our presentation. Gerd had introduced the contactless control by the magnetic forces in different applications, especially in electrochemical process where the current density required by the Lorentz force is uninvisible. And for the magnetic gradient force, it could support the structuring even when the ions are diamagnetic by properly designing the electrolyte composition. And we see that it is promising magnetic gradient force might support the synthesis of nanostructures, but the global flow in the cell needs to be minimized. The micro-scale experimental design needs to be proper. In addition, in our group, there are also some further applications of the magnetic field, like the extraction of rare earth metals using the magnetic gradient force or microfluidic flow control. And a topic that I personally find very fascinating, that controls the oxygen in water electrolysis, because oxygen is produced as an anode, and it is a paramagnetic material, so it will react to the magnetic field directly. And I have been working on this a little bit and see that magnetic gradient force can actually change the dissolved oxygen distribution a lot, and this might have an effect on the oxygen bubbles and so on. So I want to thank you very much and look forward to comments and questions.
Maybe make come here for the questions. And if you agree, Gerd and Mengyuan, I suggest that we ask those questions to Gerd and then to Mengyuan, so we have a session. Sorry, go ahead. Is the microphone on? Do you see that the microphone is on? Okay. So I suggest we first ask questions to Gerd and then to Mengyuan. So I have a question for you, Gerd. First of all, thank you for a very nice talk. You mentioned the parasitic effect of the inert ions, and you mentioned that this was related to the the maintenance of the electrical neutrality.
Yes.
But electrical neutrality is always there, even if there are no additional ions. If you are
Yes.
have a copper solution, you have positive copper ions. You must have other negative ions. So
Yes.
why is this effect only there with the inert
So
particles?
it is there because you have two types of cations, and there's a certain degree of freedom how the concentration of both arranges in the electrolyte in the vicinity of the electrolyte. That's the point. It's not about the existence of the neutrality itself. It is that by adding more ions, you get more degrees of freedom, and then it comes to what we saw.
Okay.
So in that case, it's a supporting electrolyte which is being used quite often in order to maintain a high electrical conductivity in the cell, and this then gives rise to this opposite concentration boundary layer, which leads to the effects that we saw.
I see. Thank you. Thank you. Wei?
Thank you, Professor. It's very good presentation. I may have one question about the motivation of doing the magnetic field in water electrolysis. So you said that you can split the hydrogen and the oxygen by applying the magnetic field? Or
No.
So that's just the motivation for the research of water electrolysis, not a magnetic field.
Yeah, so we want to, the motivation for applying these magnetic forces is to shear and advect the bubbles out of the electrolyzer quickly in order to reduce the losses. That's the motivation.
Okay. So it's not possible with the Lorentz force to split the two different kind of gas bubble?
No, it's a volumetric force that is
Okay.
acting
Okay.
on the conductive electrolyte.
Any more questions for Gerd? So there are no more questions for Gerd. I have one more question for you. At some point in your talk, you showed how if you naively apply the magnetic field, you create a flow which is parallel to the boundary, and you don't enhance the process. But then you described the technique to actually enhance the process, and I missed that step. What was the idea to really make the magnetic field
Maybe
efficient?
we go back in the slides.
Yes.
Which one do you mean? Which?
Just the
case?
beginning of the effect of the magnetic field.
Just in the beginning. Okay.
In your talk, of course. So.
Yeah.
Yes, so now next.
Here.
Next. No, I think it was next. Yeah, again next. Okay,
No,
next.
maybe it was here. Do
No.
you mean this?
No, I think it was the next.
So
Next.
earlier or later?
Next, later.
Later, okay. Sorry.
Later. Yeah, so maybe nearby, maybe the next one. Yes. Okay. Well, maybe here. So it's a magnetic field steering effectively
Yes,
and create mainly a horizontal flow.
yes.
So how do you circumvent that effect? How do you make them more efficient?
Yeah, I mean, what I wanted to say here is that when we started to investigate this, we started with applying homogeneous magnetic fields, and we found out that doesn't work very well. So the best or the strongest effect that is being achieved in terms of enhancing the current as an indicator is indeed a vertical magnetic field. And there's a sketch here. You see how to say how the boundary layers are evolving on both sides of the electrodes. And because of the different thickness, you have a different magnitude of the electrical current in these areas. And then you have the Lorentz force, right? It's roughly speaking balanced at mid-height, but it's not balanced at the top and at the bottom region, which leads to horizontal circulation in opposite directions. And this doesn't bring much advancement to this. Of course, this is at a relatively low Reynolds number, so this is the basic effect, okay? But the modified magnetic field that I show on the next slide works much better because it actually stirs in the vertical direction. In case you do a homogeneous horizontal magnetic field, you can check how to say it tries to accelerate the electrolyte at both sides of the electrode in the same direction, which doesn't give you a circulation, basically.
Maybe we should see the next slide to see how it's quantified.
Yes, so here it's horizontal magnetic fields which are being directed out of the paper plane into the paper plane, and this gives a supporting stirring at both sides, which then leads to this swirl.
Okay, and so this B here is the buoyancy force.
No, this is how to say the amplitude of the component of the magnetic field in this horizontal direction versus distance between the electrode.
I mean
It
the
shows
small b in the box here.
the small b. So this is just the gradient.
Okay.
Yeah. Interestingly, one could ask if there's a gradient force acting here, but it's not, because the gradient of the field is being directed electrode normal, similar to the gradient of the species. So one wouldn't expect much effect here. It's dominated by the Lorentz force.
So sorry everybody for this very long question. There are other questions for Gerd. Okay, maybe we can switch the question for Mengyuan. Is there a question for Mengyuan?
In the 38th slide, there was a graph showing comparing numerical results with the simulation, and in the tip,
This one?
in the vertical U component, you have a higher values with the simulation compared to the experimental. Why do you think that's the case? Or why do you think that the simulation doesn't really simulates the experiments in the tip?
Thank you for the question. Actually, this also confused us, and our possible explanation is that in the experiment, the lowest point of the coordinate is determined by the lowest particle that can reach inside the fluid. It might actually not be the real lowest point of the cell. So we see that here we have very high gradient of the flow, so it increases from 0 in very short distance to a large value. And we thought maybe there's a small shift in the vertical coordinate system, so that these 2 points, they have difference in the velocity.
So there's an experimental grid in the grid size error. It's not taken into account in the
Kind of
size error of the PIV measurements.
Yes. So, for example, as it could be that in the experiment, the lowest points of this distance is actually larger than in the simulation, because maybe the lowest the coordinate system is located here, not really at the cone bottom, because of the particles that can be tracked in the experiment. So, yeah.
Other questions for Mengyuan? Yes, Wei.
Yeah, I see that you could manipulate the production of the nanostructure, the nanocone. I see that the typical diameter of the nanocone is 70 nanometers. So how do you manage to control this diameter of the nanocone?
Yeah, the 70 nanometer is in the work of Katharina Brinkert, and in our experimental collaborators, they are kind of like, I remember, yeah, like some 100 nanometer size kind of, and in this, we don't really control the bottom side of the cone. So the capping agent is added, and then with this initial roughness that I said before, that when the surface is before the deposition, this initial roughness, I think they are determining the basic size of the cone. Usually they are kind of this size scale.
Then my following question would be that is it possible to control the apex angle of the cone during your production?
Mm-hmm. Yeah, so our aim is that, like, with the magnetic field, we could make the apex angle smaller, so the cones should be sharper. And in addition to that, you could like use a higher current, then usually cones will also be higher, the surface will be more rough, and you could maybe change the electro composition and so on. Yeah, one needs to like try different parameter combination and find the best way to get the desired morphology of the cone.
So we had a lot of questions, and maybe there are some more. No, no more questions from the room. I have many questions for both of you, but I will maybe ask them in private so that we can close this session now. So thank you again for your talk.